The next talk title is WristLens, enabling single-handed surface gesture interactions for smartwatch using optical motion sensor by Hui-Shyong Yeo.
Okay.
Could you start?
Okay. Hello. Thank you for the introduction. I'm Yeo from St. Andrews. Can you see my screen?
Yes.
Yes, okay. This work is done in collaboration with my colleagues from KAIST and Tokyo Institute of Technology. I will be presenting WristLens, a system to enable single-handed surface gesture interaction. First, let me show you why do we need the WristLens. For example, when you are on the move, taking out your phone to check messages or changing a song can be dangerous because you are not looking at the road in front of you and you may fall down. With WristLens, you can use on-body gesture to control your device, such as making left or right direction, or draw different shapes to activate different commands. With this, you can concentrate looking at the road in front of you. It is also not limited to just your body parts. You can also use it with almost any surface. For example, you can use it to control the smartwatch itself or to control another device, such as a TV here. Here, I show you that how it can be used to input text using gesture keyboard. So the on-body gesture interaction is the main topic of this paper, but there are many other interesting use cases that I want to show you. For example, here, you can quickly measure any object in any shape. And how can we achieve this? We use the optical sensor to measure the distance travel, and we use the gyroscope to measure the orientation continuously. By combining these two sensors together using sensor fusion, we can achieve 3D measurement. In another use case, let's say that you are using a mouse on your right hand typically, and you wear a smartwatch on the left hand. Then you can use bimanual interaction technique, such as pin to zoom or rotate. If you are using a stylus to draw something, the left hand can help control the brush size or brush color or other parameters. And it is very easy and continuous control. Normally, you would need to buy a surface dial to do this, or you can use the on-screen control. Okay, so there are more use cases in the paper, so please refer to the paper. We made several hardware prototypes. The first version was big and ugly, and the bottom part was extruding. And it has to be connected to the laptop and Arduino, so we didn't include this in the paper. The second version is much better. The bottom part is flush and doesn't extrude so much. It is self-contained. It has a wireless capability. It has battery and microcontroller, so the processing can be done locally. So why do we put the sensor in the strap? And there are a few inspirations. Nowadays, there are many products that it's called smart strap. It has the sensors, it has the display and the processing unit. So you can use this kind of smart strap with your traditional watch without buying a new smartwatch. All you need to do is just change the strap into a smart strap. As you can see here, the optical sensor actually, it is quite small. So I believe it can be easily embedded into a smart strap. The technology is also very cheap and robust because it is used in all the computer mouse nowadays. And most importantly, it creates a unique opportunity to allow us to slide on any surface with the wrist for interaction. I will quickly talk about some related work. For example, Magic Ring uses optical sensor, but it adds another micro camera. So it can clearly see the surface and even recognize some embedded QR code. 3D Touch uses only optical sensor, so it is very similar to us, but they are focusing on the fingertip interaction. Light Ring uses gyroscope and infrared sensor to detect a mouse-like action. But the key difference here are they are all focused on the fingertip interaction. And we argue that wearing a smartwatch on your wrist is more commonly accepted than putting a device on your fingertip. Secondly, they all require tethering to a computer, but WristLens is fully wireless and self-contained. We conduct a user study. We chose the 3 locations or the body parts that are inspired by previous work. The details of the study are in the paper, so please refer to the paper. In the user study, the participants wore a diverse type of clothing, and the sensor readings are also dependent on the surface properties such as the area size, the flatness, and the material type. So loose clothing can cause noisy readings because it tends to create folds that makes the sliding movement difficult because of friction. Specifically, sliding movement that stretch the cloth are easier to perform than the movement that fold the cloth together. As I said before, it works on almost any surface, but not every surface. Because, for example, on the reflective surface, such as glass and mirror, the mouth sensor, the optical sensor will not work well. And actually, in our study, there was one pen that didn't work well. The sensor reading was quite noisy. Here are some visualized gesture trails, each color for different body parts. And there are a few observations, so let's look at one. So we can see that different participants perform the same gesture with inconsistent direction and orientation, even for the same body parts. It means that the users have a different perception of what is left and right, or what is top and bottom on their body. And they may invert the one or both axes when they are prompted to perform a gesture. Also, let's look at the participant number 7 because his data looks quite clean. So we can notice that the blue color, which stands for the other arm, is quite short. It is because the surface area of the arm is quite smaller than the abdomen and other parts. So the gesture is much shorter. And it was also more difficult to perform on this small area. Here are some results. On the left, we can see the completion time. And the other arm has the lowest completion time. But actually, it doesn't mean that the gesture is fastest on the other arm because, as I mentioned before, the surface area is smaller, so the gesture is also shorter, hence the shorter time. On the right side, we can see that the accuracy is higher on the abdomen part. It is because the area is bigger, so the user can draw well on the flat and big surface area. And here are the confusion metrics for the 8 different gestures in the study. Please refer to the paper for more details. In overall, the directional gestures are more accurately recognized, but less so for the shape gesture. And there are several factors that contribute to this result. Because naturally, the shape gesture are more difficult to draw consistently than the simple directional line gesture. And this issue becomes more prominent when gestures are performed on the body due to surface friction and different spatial orientation of the user. Most importantly, participants perform the gesture with their non-dominant hand because they wear the watch on their non-dominant hand, and which by nature does not possess the same fine motor skill as the dominant hand. We also asked the standard NASA TRX questions to the user, and we also asked 3 more questions, including the comfortability and social acceptability to perform this gesture in front of friends or in front of strangers. And from the result, it can be seen that the abdomen part has the lowest perceived workload, followed by the thigh and the other arm. However, abdomen was also voted by the participant as the least socially acceptable location to perform this kind of gesture, either in front of friends or in front of strangers. We can also see that the arm is also not so comfortable. Therefore, the thigh area might be the participant's most preferred body location. It maintains a balance between perceived workload and the social acceptability. For limitation, the current form factor is still quite big, and it can be further improved and miniaturized. The evaluation was also limited with the participant standing still. Therefore, we cannot generalize our results for situations in which the user is on the move, such as walking or running. And there is also no surface recognition capability. Therefore, we could not enable context-aware interaction, such as body shortcuts. In summary, WristLens enables surface gesture interaction using a wrist-worn device, such as a smartwatch or fitness tracker. Our evaluation results shows that directional gesture can be accurately recognized on different body parts, but less so for shape gesture. Participants feel that it is comfortable and socially acceptable to perform this kind of gesture on the thigh and other arm in the public area, but less acceptable on the abdomen area. Finally, we envision such type of sensor, when included in the future wearable device, unlocks a high potential interaction modality. That's all for my presentation. Thank you for your attention.